Hey everyone, welcome to day 3 of Liquidity 2020. We are kicking things off with Tom from StarkWare. He'll be doing a talk on layer 2 scaling, interoperability. Once he starts talking, can you guys confirm in the chat that you can hear him?
Hi everybody, good evening or good morning, and thank you for having me here. My name is Tom Brand. I'm a product manager and a researcher at StarkWare. Before I begin, I just wanted to say this is like all this Corona time is a bit hectic time. I don't know, 20 minutes ago I put my baby to sleep, and then I have to get my other child out of the room, and now I'm here, and I have to do the context switch. So this is on one hand, and on the other hand, it's kind of nice because it's much more intimate. There's no big stage, it's just me sitting here, the same place I seated a few hours ago, and describing to you what we do in our work at the same place. So yeah, anyway, I'll stop rambling and let's get to what you came here for. So today we're going to talk about layer 2 scalings, and specifically how do we plan to solve the problems it creates from interoperability point of view. So I will talk a little bit about StarkWare, then I will describe our layer 2 scaling solution. Again, very shortly. If you have any questions, don't be afraid to ask. And then I'll describe in a stepwise approach how we plan to solve those interoperability issues one step at a time. So let's begin. Okay. Yeah, okay, it moved. Okay, so StarkWare is a startup based in Israel. It was founded almost 2.5 years ago, and we are already close to 40 team members, with the majority of us are engineering and product. We had funding in 2 equity rounds of approximately $36 million, and also a very generous grant from the Ethereum Foundation, which was for us to develop an open source Stark prover, which David, also from StarkWare, will be speaking about it tomorrow at 1 hour from now. And our first product was StarkX, which was a layer 2 scalability solution. And our customers for StarkX are Diversify, which already have a deployed exchange working on mainnet, Immutable, which will hopefully soon will have one, DYDX and Paraswap. And today we're gonna discuss how we take all those StarkX deployments and turn them into a connected ecosystem. So this is a bit intimidating slide. I won't go into the details. So just to give a very quick overview on StarkX. So StarkX is a layer 2 scalability solution. It uses validity proofs, which are also known as ZK proofs. And like all other layer 2 scalability solutions, its main purpose is to offload both computation and storage from the layer 1 and do them on layer 2, and still maintain the security that layer 1 gives us, right? So generally speaking, how we do it, here we have the Ethereum, we have some off-chain services, and StarkX maintain his state in the off-chain, and on-chain, we have only a commitment to the state, a root, and we push state updates to this commitment, representing state updates in the off-chain state. Now, how do we make sure that those state updates are correct? We also generate proofs attesting to the validity of those state updates. Okay, so whenever a state is updated in a StarkX system, a proof attesting to the validity of this state is also submitted to the chain. And so every state is always final. How do we achieve scalability with this kind of solution? The way we do it is by batching together many user interactions into one state update. And since the proofs are sublinear at the size of the computation, uh, um, the actual cost on chain is also polylogarithmic in the size of the computation. Also, the cost of making a state update on chain is polylogarithmic in the actual computation that was done off chain. So this is very, very fast. The main thing you need to know is that users do transactions off chain when they want to interact with Ethereum. We do a state update, and it is accompanied by a proof. And I think this is mainly it. Now, this is very good. It creates us a massive scalability. As you can see, this is some of the key features of StarkX. But for example, from scalability point of view, we demonstrated on mainnet a tremendous scalability of 18K transfer per seconds and also 9K trades. We demonstrated various functionalities as minting and burning and token distribution. StarkX support transferring and trading in multi-assets. And as I've said, the scalability is gained through the gas reduction that we achieve by the proofs. More than that, StarkX and the technology that StarkWare is developing supports general computation. So I think it was 2 weeks ago, we announced, maybe more, we announced the Cairo, which is the language that we are using and the architecture of a proof system that we are using, which allows us to prove, to generate proofs for arbitrary logic. And we, in the system, for example, that we are developing with the DYDX, we demonstrate exactly how we can custom tailor a system for the customer needs. And the last feature is what we're going to talk about today, but is interoperability between StarkX systems. So let's first understand what is the problem. The problem is that our apps, which are deployed on mainnet, in the naive implementation, are siloed, and moving between them or moving to the layer 1 is inefficient. Let me explain exactly what I mean. So here we have at the bottom the Ethereum blockchain. Here we have the StarkX ecosystem, and we have 2 applications. Now, just to compare some interactions, so when users want to, for example, trade in an off-chain system, it is very, very fast. As you can see here with the 3 rabbits. It is very cheap. An on-chain transaction is a bit, it is more expensive, much more, and is also more slow because it is only in a block. And the 2 main things that we need to understand is that there's no way to interact between those 2 applications. And going on-chain, for example, if Alice wants to withdraw her funds to her on-chain account, usually what you need to do is to do it through a proof. And this takes more time than trading or a chain transaction. It can be on the orders of tens of minutes. And it is and it costs on the same order of magnitude as a regular ATM transaction, for Alice, I mean. Okay, now that we understand the problem, let's see how we solve those 2 problems. First, how do we interact with Ethereum in a fast and efficient way? And then, how we transfer funds between 2 StarkX applications in a fast, efficient way. And I forgot to say it, but you know we're in blockchain. So what we describe here is a trustless mechanism. And let's see how. So step 0, which is already implemented in our upcoming version, which at the end I will share a bit more timelines, but it will come in the coming weeks. It's fast and trustless exit. So the purpose of this step is to allow users to exit from the system in 1 Ethereum transaction. What does it mean? It means that we are not dependent in proofs, right? And the cost is 1 Ethereum transaction. And furthermore, we want to allow users to interact with Ethereum, not only to transfer funds to their account, but maybe to see more interactions, and we'll see in a second. And in order to facilitate those requirements, what we use is a conditional transaction, okay? Conditional transaction is an off-chain transaction, means it is a transaction that is done in the off-chain state, not on Ethereum. And the special property of a conditional transaction is it is valid only if an on-chain transaction has occurred. Okay, maybe it's a bit confusing. Let's see a diagram. So again, we have here one StarkX application in the Ethereum blockchain. And what we want to achieve here is for Alice to move her funds from her off-chain account to her on-chain account. What we do is we use a liquidity provider which has available funds on-chain, and what I just described a conditional transaction. So Alice is signing a conditional transaction, transferring some amount, let's say, of ETH to the liquidity provider, when the condition of this transaction is that the liquidity provider will transfer funds to Alice, right? So this transaction is not valid, meaning we can't generate a proof to it unless the liquidity provider transfer funds to Alice. So once the liquidity provider has this transaction, he can execute the transaction on chain, and then the transaction off chain can be executed because the condition is met. Right. So what we achieve here is a fast and trustless exit for Alice, but we can also expand it. So this is just for comparison, but what we just described is Alice withdrawing funds to her account on chain. But we can also do the condition on a much more complicated Ethereum transaction, for example, an AMM trade or lending tokens to Compound, for example. So Alice can say, I will give DAI to a liquidity provider if he will lend them on Compound and return to me CDAI. So what we achieve here is that we can now use all the funds that we have in the StarkX system to interact with Ethereum in a fast and trustless manner. Okay? And I hope this was understandable. If you have questions, please ask. Now, we solved the first problem. And the second problem is how we construct bridges between different StarkX applications, right? So again, we have here two applications. And we saw how we can do a fast withdrawal, how we can do a fast exit. So if we want to move funds from Alice account on up to application one, we can do it in a naive implementation, right? We can do a fast withdrawal. And then Alice can immediately deposit the funds to the application. The problem with this approach is that, first of all, it costs a lot of money, meaning for each transfer you have to do at least 2 Ethereum transactions, which today is not negligible, and it is also not very fast because you have to move through Ethereum. And the idea to solve this is also to use conditional transactions, but now we condition on an off-chain transaction. Before we said we condition an off-chain transaction on an Ethereum event. Now we are saying we have an off-chain conditional transactions, which is the condition is now a different off-chain transaction. Okay, let's see what happens here. It is a bit more complicated, but you'll be fine. Okay, so again, we have here Ethereum. We have here two applications, and we have here Alice with their account on application 2, an account on application 1, and we have a liquidity provider which has an account on application 1, an account on application 2. Note that there is no accounts on Ethereum that are involved, right? So the first step is that Alice signs a conditional transaction. But now the condition is not the liquidity provider transferring funds on-chain to Alice, but the liquidity provider transfer funds on a different application to Alice. Now, once the liquidity provider has this transaction signed, he knows he can transfer the funds, so he executes a transaction. And now this is a bit more tricky part, but I promise you it's fine. So the problem here is that application 2 needs to know about what happened on application 1. And as we've said before, it's not the same state, and they cannot communicate. So they somehow need to verify it through the blockchain. So let's see what happens. So application one batches transaction, as it always do, and post a state update. As part of this state update, one of the transactions that is included in the state update is the execution of this transaction. Now, once this application sees this transaction is indeed final, it can execute the conditional transaction, transferring the funds from Alice to the liquidity provider. Now, we need to finalize this batch. So what happened is that we have, I just moved it so it will be more clear. We have a state update from application 2. And what happens in this state update is that the on-chain contract checks in the other application contract if the transaction was indeed included. If it was included, the proof gets accepted and the state is finalized. If it was not included, meaning Alice didn't get her funds on application 1, the state is reverted and Alice gets back her funds on application 2. Okay, so what we get here is that Alice, in a trustless way, receive her funds on application 1. And first of all, it was very cheap because we didn't go through Ethereum. And it was very fast because from Alice's perspective, all she did was sign an off-chain conditional transactions. And then immediately the transaction was executed on the other application. Okay, does anyone have a question about it so far? Very good. Okay, we're approaching the end. Now we need to understand, so we said it was very inexpensive from the perspective of Alice, but let's understand if there are maybe other costs that are involved in this process. So the first cost that is involved here is the capital efficiency cost. And what I mean by that is that we are using a liquidity provider to enable the bridge, right? And this liquidity provider has some cost involved with the capital that he's providing. And here, the effective parameter is the finality of the state transition. And so what I mean by that, we need to understand, I'm going back to the diagram, and we need to understand when the liquidity provider gets his funds and he can use it for anything else. He can use it when the conditional transaction was executed on application 2. Now, when this conditional transaction can be executed, once this application see that the state of application 1 is finalized. Now, as I've said before, those state updates can be very, very frequent. The generation of the proof can take, depends on the size of the batch, but it can be every few 10 minutes, right? So the locking of the funds of the liquidity provider is on the order of tens of minutes, which is very short. Now, the other cost that we have here is the on-chain cost, right? If you remember, the state update of application 2 involved somehow validating on-chain that the transaction was included. Now, you may think that this is a big overhead, but actually it is quite a small overhead because I'm not getting into the details. We will publish it soon, but most of the validation is done off-chain and is done by the proof. And the actual validation on-chain is very, very small. And it's actually constant per state update. And it does not increase with the number of transactions. So what we get here is that both the cost of the liquidity provider and the on-chain cost of validating the transaction was indeed included is very small. This is the end of step 1. Step 2 for us is increasing those bridges to other L2 technologies. We do not believe that, at least in the following years, there will be only one layer 2 scalability solution which will rule them all. And so what we plan to do as the next step is to define a standard which will allow anybody who implement what are the minimal requirements to construct these trustless bridges between StarkX and their L2 technologies. So just I will brief through it because it is the topic for a whole other presentation, but very generally speaking, you need to have two things in order to be compatible with this protocol. One is you need the ability to prove the execution of a transaction in your state. For example, you can have a history tree representing all the transactions that occurred in your system, right? So this is the first requirement. And the second requirement is the ability to condition a transaction in your system on the execution of a transaction in a different system, right? The same way we did in what I described. And if we look at the leading technologies that we have today for layer 2, then these requirements work pretty natively with other ZK rollups because the state structure and the cryptographic primitives that are being used is quite efficient in both cases. It can also work with optimistic rollup, but there we have much less efficient. First of all, from the perspective of the liquidity providers, because again, finality is the queen, and in optimistic rollups, the finality times are much higher. If we said the tens of minutes, there it can be on the order of days. So we have a factor of almost 1,000. So this is also the factor of the cost for the LPs. And the cryptographic primitives that are being used are not always proof sufficient. Okay, so this is a very quick summary of the last step. Now, I'm running out of time. So this is fun because we're at the last slide. So just talking about timeline, step 0, which we described as fast trustless exit and also interaction with the Ethereum, is ready now and will be deployed in the coming version of Diversify in the coming weeks, and will also be included in the deployments of Immutable, the YDX, and of Paraswap. Step 1 will be shipped in the next version of StarkX, which is pretty close. It will be in the Q1 of next year. And connecting to other L2s is hopefully from then and onward. Yeah, and that's it. So thank you very much. I'm very excited for everything that's happening in this space, and specifically to how the StarkX ecosystem will look like in a few months from now. This is my handle on Twitter and Telegram. Feel free to reach out and ask whatever you want, and have a good evening or morning or wherever you are. Thanks. And I mean, I don't know how to close it, but it's good time for questions. Oh, there's a question. Okay, so Jacob, and forgive me if I'm not pronouncing it correctly, but he's from the Galactic Council, is asking, what about interoperability with other chains like Polkadot parachains? So this is a very good question. With other chains, there are many possibilities. One of them is to actually deploy proofs verifiers on those chains. And then you can have 2 places which are connected to your state, and on both of them you can update the chains. But this is a totally different problem, because now you have problems of synchronicity between the state updates. But generally speaking, I think it is okay. The first part of deploying a Stark verifier on another chains is something that we know we want to do, and it's not a problem. And then you have the question on how you create the synchronicity between the state updates on Ethereum and and other chains, and this is something that I haven't thought about a lot, and I think it's a very interesting problem. Hi, Chloe. Chloe is asking, is there any work being done allowing Viper to be used with Cairo, or is Solidity the only language being implemented currently? So, yeah, Cairo is okay. So I will give a bit of a background. Cairo is the architecture of our proof system that we are using, which allows us to have one verifier and write Cairo programs to it, allowing us to use to basically write programs and not errors that we had to write before. Now we demonstrated 2 weeks ago how we take a simple Solidity code and compile it to Cairo, and I mean we didn't choose either Cairo, either Solidity or Viper, and I think there are advantages to each choice. In the coming weeks or month, we'll start to share more about Cairo, and once it's open, I think that anybody will be able to start writing those compilers. So, I mean, everything is open. Thanks. Any more questions? Okay, thank you. Not sure how I close it.
Awesome. This was a really great talk. So we're going to transition to our next session now. Do you have any final words you want to share?
I mean, I gave my at the beginning. I gave my a bit on
I think someone asked a
work
third
and family
question.
life.
Oh,
The
someone
corona.
asked a third question if you want to answer.
Oh, nice. Okay. So Sora, hi. Do Zk rollup applications share the same group of aggregators for the proof generation? I'm not sure I completely understood the question, but I will try to answer. And correct me if this is not what you asked. So different Zk rollup applications on our ecosystem, StarkX. So they use the same technology, and so they use the same verifier on chain. And looking into the future, again, maybe you'll hear about it more in the coming weeks, but they will also be able to share proofs, meaning we'll be able to take programs from different applications on the StarkX ecosystem and to generate one proof for all of them, and then they will be able to share the cost of the proofs. When you're looking at other Zk rollup applications, then there you have a wide variety of proof types, and different proof types do not share the I'm not sure this is the correct term, but do not share the aggregator for the proof generation. So they will be in different proofs, not using the same verifier. But for StarkX application, we have the same verifier, and we can batch those proofs together to one proof, and each application is represented by its own Cairo program. Hope this answered your question. If not, you can reach me. I'll be happy to answer.
Tom, this was fantastic. Thank you so much for taking the time, and have a wonderful weekend, remaining of your weekend. All right, bye.
Beginning